Close your eyes for just a moment. Imagine you're standing in a field, far from the city lights. The grass is cool beneath your bare feet. Above you, the sky is a canvas of infinite darkness, punctured by thousands of tiny lights, some steady, some flickering, each one a world unto itself. You've looked at this sky your entire life, but tonight, something feels different. Tonight, you're going to truly see them, not just as points of light, but as worlds, as places, as stories written in stone and gas and ice orbiting in the eternal silence of space. Welcome, dear wanderer, to the Midnight Explorer. I'm here to take you on a journey, not across miles, but across time and understanding. Tonight, we'll travel to places no human foot has touched, yet places that have shaped every moment of human history. We're going to explore the planets, not with telescopes or spacecraft, but with something older and more powerful: stories. So settle in, pull your blanket a little closer, let the worries of the day drift away like clouds, because tonight we're going to discover how humanity learned the truth about the wandering lights in the sky, and in doing so, discovered truths about ourselves. Let me take you back, far back, before cities, before writing, before even the wheel turned for the first time on ancient roads. We're going back to when humanity was young, when we huddled around fires that pushed back the darkness, and the night sky was our first television, our first storybook, our first glimpse of something greater than ourselves. Picture a night, perhaps 50,000 years ago. A small group of people, your ancestors and mine, sits beneath a sky so clear, so brilliant, that the Milky Way casts shadows. They've eaten their meal, the fire crackles, children lean against their parents, and someone, perhaps an elder with weathered hands and eyes full of memory, points upward. "Look," they might have said in a language lost to time, "the lights that wander." Because that's what our ancestors noticed first. Most stars were fixed, eternal, unchanging. Night after night, year after year, the same patterns wheeled overhead. The ancient Greeks called them the fixed stars, and they seemed to be painted on a great celestial sphere that rotated around the Earth. But there were others, lights that moved. 5 of them, visible to the naked eye, drifting against the background of stars like travelers on a road. They moved slowly, deliberately, sometimes even seeming to stop and reverse direction, a phenomenon we now call retrograde motion, but which must have seemed deeply mysterious, perhaps even magical, to ancient observers. The Greeks called them planetes, wanderers, and from that word we get our modern term planets. But long before the Greeks, other civilizations were watching. In Mesopotamia, between the Tigris and Euphrates rivers, where some of humanity's first cities rose from the fertile soil, priest astronomers climbed ziggurats, massive stepped temples, to watch the skies. They kept meticulous records on clay tablets, tracking the movements of these wandering lights with remarkable precision. They saw omens in the heavens. They believed that the gods spoke through the movements of celestial bodies. When a bright wanderer appeared near a certain constellation, it might signal war. When another made its retrograde dance, perhaps it foretold the harvest. But they were doing something else too, something revolutionary. They were discovering patterns. They were learning that the universe, for all its apparent chaos and mystery, followed rules. The wanderers moved in predictable ways. If you watched long enough, took careful enough notes, you could begin to anticipate where they would be. In ancient Babylon, around 1600 BCE, astronomers compiled the Venus tablet of Amisaguqa, one of the oldest surviving astronomical documents. It tracked the appearances and disappearances of the bright morning and evening star that we now know as Venus. They didn't know they were looking at a planet. They thought they were watching 2 different celestial objects: Ninciana, the Lady of the Heavens in the morning, and Dilbat in the evening. The same phenomenon was observed in ancient China, where Venus was called Ginseng, the metal star, associated with the element of metal in their five-element cosmology. Chinese astronomers, working independently, developed their own sophisticated systems for tracking planetary movements, seeing in them the workings of cosmic harmony. In ancient India, astronomers wove the planets into their spiritual cosmology. They called them the Navagraha, the 9 celestial influencers. Each planet was associated with a deity, a color, a gemstone, a day of the week. Mars was Mangala, the warrior god, red as blood. Jupiter was Guru, the teacher, bright and benevolent. Saturn was Shani, slow-moving and associated with karma and discipline. And perhaps most beautifully, in the ancient civilizations of Mesoamerica, the Maya, the Aztec, astronomers who had never spoken to their counterparts in Babylon or China independently discovered the same patterns. They tracked Venus with extraordinary precision, integrating its cycles into their calendar systems and religious observances. The Maya could predict Venus's movements with an accuracy that wouldn't be surpassed until the Renaissance. Think about that for a moment. Across the world, separated by oceans and mountains and thousands of miles, humans looked up and saw the same wandering lights. And they all asked the same question: what are they? Different cultures gave different answers, but they all sensed something profound. These lights were not like the fixed stars. They were special. They were messengers, perhaps, or gods themselves, or windows into divine will. But what were they really? What were these lights that moved through the heavens, sometimes bright, sometimes dim, sometimes racing forward, sometimes appearing to slide backward against the stars? To answer that question, humanity would have to undergo a revolution, not just in understanding the cosmos, but in understanding our place within it. The ancient watchers gave us our first knowledge, that patterns exist, that the universe can be understood, that careful observation reveals truth. They couldn't have known that these wandering lights were worlds, vast spheres of rock and gas, orbiting the same star that warmed their skin each day. But they took the first step. They looked up, they wondered, and they began the long, slow journey towards understanding. Now, let's walk forward through time. The centuries roll past like pages in a book. The Roman Empire rises and falls. The Middle Ages settle over Europe like a long twilight. Knowledge is preserved in monasteries, in the Islamic Golden Age, in the courts of Chinese emperors. The planets continue their wandering dance, and humans continue to watch, to wonder, to theorize. But there's a problem, a big one. For all the sophisticated observations, for all the mathematical models, there's a fundamental assumption that almost everyone shares. Earth is the center of everything. The sun, the moon, the stars, and those mysterious wandering lights all revolve around us. It's called the geocentric model, and it makes intuitive sense. After all, when you stand on the Earth, you don't feel it moving. The sun clearly rises in the east and sets in the west. The Earth feels solid, stable, unmoving. The Greek astronomer Ptolemy, working in Alexandria around 150 CE, had refined this geocentric model into a sophisticated mathematical system. The planets, he proposed, moved in small circles called epicycles, while simultaneously orbiting Earth in larger circles called deferents. It was complicated, requiring intricate calculations and adjustments, but it worked. Sort of. It could predict planetary positions with reasonable accuracy. For nearly 14 centuries, Ptolemy's model dominated astronomical thinking. It was adopted by the Catholic Church and became intertwined with religious doctrine. Earth was the center of creation because humanity was the center of God's concern. The heavens were perfect and unchanging, while Earth was the realm of change and decay. But there was always something unsatisfying about this model. Those epicycles, the wheels within wheels, seemed arbitrary, complicated. Why would the cosmos be designed in such a convoluted way? And the retrograde motion of planets, that strange backward drift, required elaborate explanations that felt like mathematical patchwork. Enter Nicholas Copernicus. Picture him, a canon in the Catholic Church, living in Fromberg, Poland in the early 1500s. He's not a revolutionary by temperament. He's cautious, scholarly, devoted to his duties. But he has a secret manuscript, one he's been working on for years, one that contains an idea so radical, so potentially dangerous, that he hesitates to publish it. In this manuscript, De Revolutionibus Orbium Celestium, on the revolutions of the celestial spheres, Copernicus proposes something extraordinary. What if Earth isn't the center? What if the sun is? Imagine the leap of imagination this required. Everything in human experience suggested Earth's centrality, but Copernicus realized that if you placed the sun at the center, with Earth and the other planets orbiting around it, suddenly everything became simpler. The retrograde motion? Just an illusion caused by Earth overtaking slower-moving outer planets in its orbit. The epicycles? Unnecessary. The whole system became more elegant, more harmonious. It was a beautiful idea, but it was terrifying too. Because if Earth moved, if we were just one planet among others, what did that mean for humanity's special place in creation? What did it mean for religious doctrine? What did it mean for everything people believed about their world? Copernicus knew the implications. He waited, he refined his calculations, he shared his ideas with a small circle of trusted colleagues, and only on his deathbed in 1543 did he finally allow his book to be published. Legend says he received the first printed copy on the very day he died, perhaps holding it in his weakening hands before slipping away, a revolutionary who would never see the revolution he sparked. But the idea was out there now, loose in the world, and ideas, once released, cannot be easily contained. In the decades that followed, Copernicus's heliocentric model spread slowly among astronomers and mathematicians. Most still rejected it. It contradicted common sense, after all, and it challenged powerful religious authorities. But a few brilliant minds began to take it seriously. One of them was an Italian mathematician and astronomer named Galileo Galilei. It's 1609. Galileo is in his 40s, teaching at the University of Padua, his mind always restless, always questioning. He hears rumors of a new invention from the Netherlands, a device that uses lenses to make distant objects appear closer. The Dutch call it a spyglass. Within weeks, working from these basic descriptions, Galileo builds his own version. And then he does something no one has thought to do before. He points it at the night sky. Imagine that moment, the first human to see the heavens magnified, revealed in unprecedented detail. What Galileo saw must have taken his breath away. He looks at the moon first. Through his telescope, as he names it, from the Greek words for far and to see, the moon is not a perfect sphere, not a smooth celestial body. It has mountains, it has valleys, it has craters. It's a world, a place, as rough and real as Earth itself. Then he turns his telescope to Jupiter, and there, like a miracle, he sees something extraordinary. 4 small points of light arranged in a line beside the giant planet. Night after night he watches them, and they move, but they move around Jupiter, not around Earth. Galileo has discovered Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, named later by another astronomer, Simon Marius. They would come to be called the Galilean moons in his honor. Do you understand what this meant? Here was direct proof that not everything orbited Earth. Here were celestial bodies clearly circling Jupiter. The geocentric model was wrong. Copernicus was right. Galileo's telescope revealed more wonders. He saw that Venus went through phases, like our moon, something that only made sense if Venus orbited the sun, not Earth. He saw spots on the sun, later called sunspots, proving that the supposedly perfect heavens were subject to change and blemish. He saw that the Milky Way was not a cloudy streak, but was composed of countless individual stars. With each observation, the old cosmic order crumbled a little more. But knowledge comes with a price. In 1616, the Catholic Church formally declared the heliocentric model contrary to Scripture. Galileo was warned not to teach or defend these ideas. For years he remained mostly silent, but in 1632 he published Dialogue Concerning the Two Chief World Systems, a book that clearly favored the Copernican view. The result was predictable and tragic. In 1633, at age 69, Galileo was tried by the Roman Inquisition. Under threat of torture, he recanted his support for heliocentrism. He was sentenced to house arrest, where he would remain for the rest of his life. But the truth was out there. The planets were not mysterious wandering lights attached to crystalline spheres. They were worlds, other worlds, orbiting the sun just as Earth did. We were not the center of the universe. We were part of a larger cosmic dance. Think about how this must have felt. For thousands of years, humanity believed Earth was the center of everything, the stage on which the entire cosmic drama played out. And now, slowly, sometimes painfully, we were learning otherwise. It was a loss, in a way, a loss of centrality, of specialness, but it was also a liberation. Because if Earth was a planet, then what were those other wandering lights? Were they worlds too, with their own landscapes, their own features, their own stories? The telescope had opened a door, and generations of astronomers would walk through it, discovering wonders beyond imagination. But Galileo's 4 moons around Jupiter, Venus's phases, Saturn's odd appearance — Galileo's telescope wasn't powerful enough to resolve its rings clearly, he thought the planet had ears — these were just the beginning. To truly understand the planets, we would need more than telescopes. We would need a new way of understanding motion itself, a new physics that could explain why planets moved as they did. We would need Ian Newton.
It's Christmas Day, 1642. In a small farmhouse in Woolsthorpe, England, a premature baby boy is born. He's so tiny, so fragile, that no one expects him to survive. His father has already died, his mother is worried and exhausted. The boy clings to life through sheer stubbornness, perhaps, a trait that will define his entire existence. His name is Isaac Newton, and he will change everything. But let's jump ahead. It's now 1665, and Isaac is 22 years old, a student at Cambridge University. Then, plague strikes. The Great Plague of London spreads outward, and universities close. Isaac returns to his family's farm in Woolsthorpe. For most young people, this would be a disaster, an interruption of education and ambition. For Isaac Newton, it becomes the most productive period of his life, later called his annus mirabilis, his miraculous year. Alone in the countryside, with nothing but time and his own ferocious intellect, Newton begins to think. He thinks about light and discovers that white light is actually composed of all the colors of the rainbow. He invents an entirely new form of mathematics, calculus, to help him solve problems about motion and change. And he begins to think about the planets. There's a famous story, probably apocryphal, but beautiful nonetheless. Newton sitting in a garden watching an apple fall from a tree. In that moment, the story goes, he realizes something profound. The force that pulls the apple down is the same force that holds the moon in its orbit around Earth. Gravity. It seems obvious now, doesn't it? But it wasn't obvious then. The heavens were supposed to follow different laws than Earth. Earthly things fell down, celestial things moved in perfect circles. They were separate realms, separate rules. Newton united them. He realized that the same force operates everywhere, on Earth, in the heavens, throughout the entire universe, and he could describe this force mathematically. In 1687, Newton published Philosophiae Naturalis Principia Mathematica, often simply called the Principia. It's one of the most important scientific books ever written. In it, Newton lays out his 3 laws of motion and his law of universal gravitation. The mathematics is dense, difficult, revolutionary, but the core insight is beautiful in its simplicity. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. That's it. That's the secret that governs the motion of planets, the fall of apples, the orbit of moons, the dance of galaxies. Newton showed that the elliptical orbits of planets, described earlier by Johannes Kepler, weren't just observed facts, they were inevitable consequences of gravity. A planet orbiting the sun is falling toward it constantly, but moving fast enough sideways that it keeps missing, tracing out an ellipse as it falls. Imagine the intellectual courage this required. Newton was saying that the same rules that govern a rock tossed in the air also govern the majesty of Jupiter, the rings of Saturn, the dance of moons around planets. There was no special realm of the heavens. It was all one universe following one set of laws. This was physics. This was science in its modern form, not just observing and cataloging, but understanding the underlying structures, the deep structures that make things work the way they do. And suddenly, the planets weren't just mysterious wanderers anymore. They were masses, moved by forces, following precise mathematical laws. You could predict their positions years, decades, even centuries in advance. The universe was not chaotic or arbitrary. It was a clockwork, intricate and beautiful, and humans had learned to read its mechanism. But understanding the laws that governed planetary motion was one thing. Knowing what the planets actually were, what they looked like up close, what they were made of, what conditions existed on their surfaces, that was something else. For that, we'd need better telescopes, bigger mirrors, better lenses, more patient observers, making careful drawings of what they saw through their eyepieces night after night after night. In the centuries following Newton, astronomy became both an art and a science. Astronomers were both mathematician and artist, sketching the features they observed on planets, noting changes, discovering new details. Saturn's rings, which had confused Galileo, were finally resolved by Christian Huygens in 1655 using a more powerful telescope. Huygens realized they weren't ears or handles, but a thin, flat disk surrounding the planet, though he couldn't have imagined the true complexity and beauty of those rings. Giovanni Cassini, working from the Paris Observatory in the late 1600s, discovered a gap in Saturn's rings, now called the Cassini division, in his honor. He also discovered 4 of Saturn's moons and made detailed observations of Jupiter's Great Red Spot, a storm so vast it could swallow Earth whole. William Herschel, a musician turned astronomer in England, built increasingly large telescopes in the late 1700s. In 1781, while systematically surveying the sky, he discovered something extraordinary: a new planet. The first planet discovered in recorded history, the first that wasn't known to ancient civilizations. He wanted to name it Georgium Sidus, George's star, after King George III. Thankfully, cooler heads prevailed, and it was eventually named Uranus, continuing the tradition of naming planets after Roman and Greek deities. The discovery of Uranus was revolutionary in itself, but it also revealed something odd. Uranus didn't orbit quite as Newton's laws predicted it should. Something was tugging on it, perturbing its orbit. This led to one of the most elegant predictions in the history of science. In 1846, mathematicians Urbain Le Verrier and John Couch Adams independently calculated where an unknown planet must be located to cause these perturbations. They sent their calculations to observers, who pointed their telescopes at the predicted location. And there it was, Neptune, a planet discovered not by scanning the skies, but by mathematics, by the power of Newton's laws. Think about that. Humans had become so good at understanding the mechanics of the solar system that they could predict the existence and location of a planet they'd never seen, based purely on its gravitational influence on another planet. By the mid-1800s, the basic structure of our solar system was known: 8 planets, Pluto wouldn't be discovered until 1930 and later reclassified as a dwarf planet. Countless moons, asteroids, comets, all orbiting the Sun, all following Newton's laws with exquisite precision. But they were still just lights in telescopes, distant and mysterious. Mars showed tantalizing hints of surface features, dark regions that seemed to change with seasons. Venus was shrouded in perpetual clouds. Jupiter and Saturn displayed colorful bands and storms. But what were these worlds truly like? To answer that question, humanity would have to do something unprecedented in all history. We would have to leave Earth.
October 4th, 1957. The Soviet Union launches Sputnik 1, humanity's first artificial satellite. It's a simple metal sphere, about the size of a beach ball, with 4 long antennas. As it orbits Earth every 96 minutes, it broadcasts a simple radio signal. Beep, beep, beep. That sound, picked up by amateur radio operators around the world, announces the dawn of the space age. For the first time in our long history, humans have placed an object in orbit. We've escaped, just barely, the gravitational well that has confined us since the first of our ancestors looked up at the stars. The implications are staggering. If we can orbit Earth, we can orbit other worlds. If we can build a satellite, we can build a spacecraft. If we can escape Earth's gravity, there's no place in the solar system we cannot eventually reach. The Cold War fuels rapid progress. The United States and Soviet Union, locked in geopolitical competition, pour resources into space programs. What begins as a technological race becomes humanity's boldest adventure. In 1959, the Soviet probe Luna 2 becomes the first human-made object to reach another celestial body, crashing into the Moon. Luna 3, later that year, photographs the far side of the Moon, the face that's never visible from Earth, hidden for all of human history until that moment. But the Moon, while spectacular, is just the beginning. The planets beckon. Those wandering lights that have fascinated humans for millennia are about to be visited for the first time. Venus is the first target. It makes sense. Venus is our nearest planetary neighbor, similar in size to Earth, often called Earth's sister planet. But Venus guards her secrets well, shrouded in thick clouds that reveal nothing of the surface beneath. In 1962, Mariner 2, launched by NASA, becomes the first successful planetary flyby mission. As it sweeps past Venus, its instruments reveal a shocking truth. Venus is hellishly hot, with surface temperatures around 900 degrees Fahrenheit, 475 Celsius, hot enough to melt lead. Its atmosphere is nearly 100 times denser than Earth's, composed mostly of carbon dioxide with clouds of sulfuric acid. Earth's sister planet is actually a vision of hell. Soviet Venera missions, designed to land on Venus's surface, face incredible challenges. The first few are crushed or cooked before they can transmit data. But Soviet engineers are persistent. They build stronger, more insulated probes. In 1970, Venera 7 becomes the first spacecraft to successfully land on another planet and transmit data from the surface. The data confirms the harsh reality. Venus is a hothouse world, with crushing atmospheric pressure and temperatures that would destroy any human technology in minutes. But for those few minutes, before succumbing to the environment, the Venera landers send back information, and later missions even transmit a few precious photographs of a rocky alien landscape under an orange sky. Meanwhile, Mars captures human imagination in a different way. Mars is smaller than Earth, colder, with a thinner atmosphere. But it has seasons. It has polar ice caps. Through telescopes, it shows tantalizing dark regions that change with the seasons, which some interpret as vegetation. In the 1800s, astronomer Giovanni Schiaparelli reported seeing canali on Mars, channels. When this Italian word was translated to English as canals, it sparked a sensation. Canals implied intelligence, engineering, civilization. Were there Martians building waterworks on a dying world? American astronomer Percival Lowell became obsessed with this idea. He built an observatory in Flagstaff, Arizona, and spent years mapping what he believed were vast canal systems on Mars, writing books arguing for Martian civilization. His work inspired countless science fiction stories, cementing Mars in popular imagination as the most likely home for alien life. But was it true? In 1965, Mariner 4 flies by Mars and transmits the first close-up pictures of another planet's surface. The images are grainy, black and white, and they show craters, lots of craters. Mars looks dead, ancient, more like the Moon than Earth. It's a crushing disappointment. Where are the canals? Where is the vegetation? Where is the life? The canals, it turns out, were an optical illusion, a combination of the human brain's tendency to see patterns, the limitations of telescopes, and wishful thinking. Mars was not populated by canal-building civilizations. But the story doesn't end there, because Mars still held secrets. In 1971, Mariner 9 becomes the first spacecraft to orbit another planet. When it arrives at Mars, the entire planet is shrouded in a massive dust storm. The mission team waits, frustrated, as weeks pass. Slowly, the storm clears. And as it does, features begin to emerge from the dust. A mountain. Impossibly large, rising 13 miles or 21 kilometers into the Martian sky, nearly 3 times the height of Mount Everest. Olympus Mons, the largest volcano in the solar system. A canyon, a gash in the planet's surface, 2,500 miles long, or 4,000 kilometers long, and up to 4 miles deep. Valles Marineris, stretching nearly a quarter of the way around the planet, so vast that if placed on Earth, it would span the entire United States. And channels. Not the artificial canals Lowell imagined, but real channels, carved by something that flowed. Water. Ancient rivers, dry now for billions of years, but unmistakable in their form. Mars had once been different, warmer, wetter, perhaps, just perhaps, hospitable to life. In 1976, NASA's Viking 1 and Viking 2 land on Mars, the first successful landings on the red planet. They carry experiments designed to search for life. The results are ambiguous, tantalizing, frustrating, but they transmit photographs of a rusty red desert under a pink sky, strewn with rocks, stretching to the horizon. For the first time, humans see the surface of another planet as if standing there. Think about what's happening here. For all of human history, the planets were points of light. Then, through telescopes, they became disks with features. And now, in just a few decades, we're sending emissaries, robotic extensions of human curiosity, to visit them, to touch their surface, to analyze their soil and atmosphere. We're turning cosmic mysteries into places, real places, with landscapes and weather and geology. In the 1960s, a young aerospace engineer named Gary Flandreau, working at NASA's Jet Propulsion Laboratory, makes a remarkable discovery. He's calculating planetary positions, as astronomers have done for centuries, but he notices something special about the late 1970s and early 1980s. The giant planets, Jupiter, Saturn, Uranus, and Neptune, will align in a rare geometric configuration. A spacecraft launched at just the right time could visit all four, using each planet's gravity to slingshot to the next, like a carefully choreographed cosmic billiard shot. This alignment happens only once every 176 years. The last time it occurred, the United States didn't exist. The next time it would happen, it would be the 22nd century. This is the window, now or never. NASA approves the mission, eventually named Voyager. Two spacecraft, Voyager 1 and Voyager 2, will be launched in 1977, carrying identical instruments and a golden record, a phonograph record containing sounds and images of Earth, a message to any alien civilization that might find it in the distant future. The Voyager missions are humanity at its best: ambitious, curious, creative, hopeful. We're sending ambassadors not just to explore other worlds, but to represent ourselves to the universe. Voyager 1 launches on September 5, 1977. Voyager 2 actually launches first, on August 20th, but takes a slower path. Both are on their way to Jupiter. Imagine these spacecraft. Each weighs less than a ton. They're fragile by any reasonable standard. Thin aluminum, delicate instruments, antennas that look like they might blow away in a strong wind. They're powered by radioactive decay, since solar panels wouldn't work in the dim light of the outer solar system. They carry 1970s computer technology, less computing power than a modern smartphone. And yet, these fragile vessels are about to transform our understanding of the solar system. In 1979, both Voyagers reach Jupiter. The planet fills their cameras, a massive world, more than twice as massive as all the other planets combined, wrapped in colorful bands of clouds swirling in complex patterns. The Great Red Spot, observed for centuries through telescopes, reveals itself as a storm system larger than Earth, rotating counterclockwise, its deepest layers disappearing into the planet's atmosphere. But Jupiter itself is almost a sideshow compared to its moons. Io, the innermost Galilean moon, is a world literally turned inside out by tidal forces. Jupiter's immense gravity, combined with gravitational tugs from the other moons, kneads Io like bread dough, heating its interior until it melts. The result is the most volcanically active body in the solar system. Voyager images show plumes of sulfur compounds erupting hundreds of miles into space. Io's surface is painted in shades of yellow, orange, and red, sulfur compounds in various forms constantly being refreshed by volcanic activity. No impact craters exist on Io. They're all buried beneath fresh volcanic flows. Europa is the opposite, a world of ice. But Voyager images show something strange. Europa's surface is incredibly smooth, crisscrossed with dark lines like cracks in a frozen lake. There are almost no craters. Something is constantly resurfacing this moon. Scientists begin to suspect what we now believe is true. Beneath that ice shell is a global ocean, kept liquid by the same tidal heating that powers Io's volcanoes, an ocean that might, just might, harbor life. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. Its surface tells a story of an ancient world, part heavily cratered, part younger, grooved terrain where some process has reshaped the surface. Callisto is heavily cratered, ancient, its surface recording billions of years of impacts, a historical record written in ice and rock. The Voyagers discover that Jupiter has a faint ring system and find 3 new moons, small, irregular bodies captured by Jupiter's gravity. They also solve a mystery. Jupiter emits more heat than it receives from the Sun. The planet is still contracting, still radiating heat from its formation 4.6 billion years ago, a warmth left over from the solar system's birth. After Jupiter, the Voyagers journey onward to Saturn. In 1980 and 1981, they arrive at the ringed planet, perhaps the most visually stunning world in our solar system. Saturn's rings have been observed since Galileo's time, but Voyager reveals them in exquisite detail. What appeared through telescopes as a few distinct rings are actually thousands upon thousands of narrow ringlets, like grooves on a cosmic record. The rings are made of countless particles, each one orbiting Saturn independently, chunks of ice ranging from grain-sized to house-sized, all caught in an impossibly thin disk only about 30 feet or 10 meters thick in places, yet stretching more than 175,000 miles or 280,000 kilometers from the planet. Why does Saturn have rings? The answer is both simple and profound. They're the remnants of a moon that ventured too close to Saturn and was torn apart by tidal forces, or perhaps material that never coalesced into a moon during the planet's formation. They're beautiful, yes, but they're also temporary, cosmic art with a limited exhibition. The rings are gradually falling into Saturn, raining down as particles spiral inward. In, perhaps 100 million years, they'll be gone, and Saturn will just be another bland gas giant. Saturn's moons prove as fascinating as Jupiter's, though in different ways. Titan, Saturn's largest moon, is the only moon in the solar system with a substantial atmosphere, thicker than Earth's in fact, but Voyager's cameras can't penetrate Titan's thick orange haze. It remains mysterious, a world waiting for future missions. Mimas, a small moon, bears a crater so large relative to its size that the impact must have nearly shattered the moon entirely. The crater, named Herschel, makes Mimas look uncannily like the Death Star from Star Wars, a case of life imitating art, or perhaps the universe having a sense of humor. Enceladus is smooth and bright, reflecting almost all the sunlight that hits it. Something is resurfacing this moon, though Voyager can't determine what. Decades later, the Cassini mission will discover that Enceladus has geysers erupting from its south pole, plumes of water ice shooting into space from an underground ocean, creating one of Saturn's faint outer rings.
Voyager 1's mission, at this point, is essentially complete. After Saturn, it will continue outward, eventually leaving the solar system entirely. But Voyager 2 has a date with destiny. The spacecraft adjusts its trajectory, using Saturn's gravity to fling itself toward Uranus, a journey that will take nearly 5 years. 5 years of traveling through the void. 5 years with instruments slowly degrading, with computer memory gradually filling with cosmic ray damage, with the sun growing dimmer and dimmer behind it. The engineers at JPL hold their breath. Will Voyager 2 survive? It does. In January 1986, Voyager 2 arrives at Uranus, becoming the first and still the only spacecraft to visit this distant world. Uranus is strange. While most planets spin like tops, roughly upright as they orbit the sun, Uranus rolls like a ball. Its axis tilted 98 degrees. It orbits the sun on its side, meaning that each pole experiences 42 years of continuous daylight, then 42 years of darkness. Imagine seasons that last longer than a human lifetime. Why is Uranus tipped over? The leading theory is a collision. Billions of years ago, during the chaotic early days of the solar system, something massive struck Uranus hard enough to knock it sideways. The collision likely happened so early in the planet's history that Uranus's moons, which also orbit in this tipped plane, formed from the debris afterward. Through Voyager's cameras, Uranus appears as a serene, featureless blue-green sphere, the color caused by methane in its atmosphere absorbing red light. There are hints of cloud features, but barely any. Uranus seems calm, almost boring, compared to the churning storms of Jupiter or the intricate bands of Saturn. But appearances deceive. Uranus, like Neptune, is an ice giant, distinct from the gas giants Jupiter and Saturn. Beneath the hydrogen and helium atmosphere lies not liquid metallic hydrogen, but a hot, dense fluid of water, methane, and ammonia, compressed under enormous pressure into exotic forms. Scientists call it an icy mantle, though at temperatures exceeding 4,000 degrees Fahrenheit or 2,200 degrees Celsius, it's hardly what we'd call ice. Voyager 2 discovers 10 new moons around Uranus and reveals that the planet has a system of dark rings, much darker than Saturn's bright icy rings, composed of organic compounds that give them their charcoal black appearance.
The previously known moons show their faces for the first time. Miranda, the smallest of Uranus's 5 major moons, is a patchwork world, its surface looking like it was assembled from mismatched pieces, smooth plains adjacent to ragged ridges and canyons. One feature, Verona Rupes, is a cliff face that drops 12 miles or 20 kilometers straight down. If you fell from the top, Uranus's weak gravity would give you 10 minutes of free fall before you hit the bottom. What created this bizarre landscape? Perhaps Miranda was shattered by a massive impact and reassembled itself, its interior partially melting and resurfacing some regions while others remained ancient and cratered. It's a reminder that even small worlds can have dramatic, violent histories. After Uranus, Voyager 2 makes its final planetary visit. 3.5 more years of travel out to the edge of the known solar system. The spacecraft is now so far from the sun that solar light takes over 4 hours to reach it. It's cold. It's dark. It's utterly alone. But in August 1989, Voyager 2 arrives at Neptune. Neptune is blue, a deep, vivid blue that makes Uranus's pale aquamarine seem washed out. This blue comes from methane, like Uranus, but Neptune has something its neighbor lacks: weather. Fierce weather. Despite being so far from the sun that it receives 900 times less sunlight than Earth, Neptune has the strongest winds in the solar system, gusts reaching 1,200 miles per hour, or 2,000 kilometers per hour. It makes no sense. Where does the energy come from? Just like Jupiter, Neptune radiates more heat than it receives from the sun, driven by internal heat sources we still don't fully understand. This planet, 4 times wider than Earth, at the frozen edge of the solar system, is a dynamo of atmospheric activity. Voyager images show a great dark spot, an Earth-sized storm system similar to Jupiter's Great Red Spot, though it would later disappear when Hubble's Space Telescope observed Neptune years later. Clouds of frozen methane hang high in Neptune's atmosphere, casting shadows on the cloud layers below, shadows visible from billions of miles away, captured by Voyager's cameras. But Neptune's greatest revelation isn't the planet itself. It's Triton. Triton is Neptune's largest moon, and it's strange in almost every way. It orbits backward, retrograde motion, meaning it moves opposite to Neptune's rotation. This suggests Triton wasn't born here, but was captured, possibly a Kuiper Belt object that wandered too close to Neptune and was gravitationally snared. That capture doomed Triton to a slow death. Its retrograde orbit creates tidal forces that gradually rob energy from the moon, causing it to spiral inward. In perhaps 3.6 billion years, Triton will cross Neptune's Roche limit, the distance at which tidal forces overcome a body's own gravity, and be torn apart, its remains forming a spectacular ring system around Neptune, perhaps even more magnificent than Saturn's. But for now, Triton survives, and it's extraordinary. Voyager 2 images show a world that looks like nothing else in the solar system. Triton's surface is young. Very few craters mar its strange terrain. There are features called cantaloupe terrain, where the surface looks dimpled and ridged like cantaloupe skin, possibly caused by repeated melting and refreezing of subsurface materials. There are long, straight valleys and ridges, dark streaks that might be deposits from geyser-like eruptions. And the temperature? -391 degrees Fahrenheit, or -235 degrees Celsius. Triton is the coldest surface ever measured in the solar system. It's so cold that nitrogen freezes solid and forms ice on its surface. Yet, even here, there's activity. Voyager images show dark plumes rising from the surface, nitrogen geysers, powered by solar heating creating pressure beneath translucent nitrogen ice, which explodes through weak spots on the surface. On the coldest world we've ever visited, geysers erupt. With Neptune, Voyager 2's planetary tour ends. Both Voyagers continue outward, carrying their golden records, their instruments gradually failing as their power supplies decay, their signals growing fainter and fainter as they journey into interstellar space. In 2012, Voyager 1 crosses the Helios pause, the boundary where the Sun's influence ends and interstellar space begins. It's the first human-made object to leave the solar system. Voyager 2 follows in 2018. They're still out there, both of them, still transmitting when they can, their signals taking over 22 hours to reach Earth. Eventually, in the 2030s, their power will run out, and they'll fall silent. But they'll keep going, coasting through the galaxy for billions of years, perhaps the last remnants of human civilization long after Earth itself is gone. The Voyager missions transformed the planets from astronomical objects into places, diverse, complex, beautiful, sometimes familiar, often alien. They showed us that our solar system is far stranger and more wonderful than we'd imagined. But they also revealed how much we still don't know. Glimpses, flybys, snapshots, Voyager gave us appetizers, not full meals. To truly understand these worlds, we'd need to go back, to orbit, to land, to explore.
Let's turn our attention inward now, to the planets closer to the Sun than Earth. These worlds bake under solar radiation far more intense than what we experience. They're hostile, extreme, forbidding. But they have their own stories to tell. Mercury is the smallest planet in our solar system since Pluto's demotion. It's barely larger than our moon. And it's close to the Sun. So close that temperatures on its sunlit side can reach 800 degrees Fahrenheit, 430 Celsius, hot enough to melt lead and zinc. Yet on its nighttime side, with no atmosphere to retain heat, temperatures plunge to negative 290 degrees Fahrenheit, negative 180 Celsius. It's a world of extremes, swinging through a temperature range of over 1,000 degrees. For centuries, Mercury remained one of the least understood planets. It's difficult to observe from Earth, always appearing close to the Sun in the sky, visible only briefly at dawn or dusk, swimming in the Sun's glare. Early astronomers struggled to discern any features on its tiny disk. In 1974-75, NASA's Mariner 10 becomes the first spacecraft to visit Mercury, making 3 flybys. The images it returns show a world that looks remarkably like our moon, a gray, airless ball covered in impact craters. There's the Caloris Basin, a massive impact scar 960 miles across, created by a collision so violent it sent shock waves through the entire planet, creating weird, jumbled terrain on the exact opposite side of Mercury. But Mariner 10 only maps about 45% of Mercury's surface. The rest remains unseen for decades. It's not until 2011 that the Messenger spacecraft becomes the first to orbit Mercury. What it reveals surprises everyone. Mercury has ice. Water ice. Inside permanently shadowed craters at its poles, where temperatures never rise above negative 280 degrees Fahrenheit, negative 173 Celsius, thick deposits of ice persist, possibly billions of years old, delivered by comets or produced by solar wind interactions with the surface. Think about that paradox. On the closest planet to the Sun, in craters that never see sunlight, ice survives. Messenger also reveals that Mercury has a magnetic field, unusual for such a small planet. Earth has a magnetic field because its liquid iron core generates a dynamo effect. Mercury, despite being smaller, must still have a partially liquid core, making it more geologically active than we'd assumed. And Mercury is shrinking. As its core cools, the planet contracts. The surface wrinkles like a drying apple, creating enormous cliffs called scarps, some over a mile high and hundreds of miles long. Mercury is literally falling in on itself. But perhaps the strangest thing about Mercury is its rotation. For years, astronomers thought Mercury was tidally locked to the Sun, always showing the same face to it,
like the Moon does to Earth. But radar observations in 1965 revealed something bizarre. Mercury rotates 3 times for every 2 orbits around the Sun, a 3-to-2 spin-orbit resonance. A day on Mercury, one sunrise to the next, lasts 176 Earth days, while its year is only 88 Earth days. The Sun does strange things in Mercury's sky. It rises, appears to reverse direction, then continues rising. Time behaves oddly when you're this close to the Sun. Venus is different. Venus is Earth's twin in size and mass, but a twin that took a very wrong turn somewhere in its development. For centuries, Venus's thick clouds prevented any view of the surface. It became a screen onto which humans projected fantasies. Some imagined tropical jungles beneath those clouds, a planet-wide rainforest. Others envisioned oceans. Venus was the morning star, the evening star, the goddess of love and beauty. Surely such a planet would be paradise. The reality is darker. We've already mentioned that early spacecraft revealed Venus's hellish conditions. But let's dwell on just how extreme this world is. The atmospheric pressure on Venus's surface is 92 times Earth's, equivalent to being 3,000 feet underwater in Earth's oceans. The air is 96% carbon dioxide, creating a runaway greenhouse effect that traps heat so effectively that Venus is hotter than Mercury, despite being nearly twice as far from the Sun. The clouds are sulfuric acid. Rain never reaches the surface, it evaporates in the heat long before landing. The sky is a perpetual orange-yellow haze. And wind. High in Venus's atmosphere, winds race around the planet at 220 miles per hour, 360 kilometers per hour, even though the planet itself rotates only once every 243 Earth days. This phenomenon, called superrotation, is still not fully understood. Oh, and Venus rotates backwards, retrograde, like Uranus, though not as extremely tilted. On Venus, the Sun rises in the west and sets in the east. Why? Possibly an ancient collision knocked it into this backward spin, or tidal effects from the Sun and its thick atmosphere gradually reversed its rotation over billions of years. But here's the haunting part. Venus probably wasn't always like this. Evidence suggests that Venus might have once had oceans. Maybe for as much as 2 billion years, Venus was more Earth-like, with liquid water on its surface, maybe even a climate hospitable to life. But something went wrong. The leading theory involves a runaway greenhouse effect. As the Sun gradually brightened over billions of years, Venus received more solar energy. This caused more water to evaporate. Water vapor is a greenhouse gas, trapping more heat. This caused more evaporation, which trapped more heat, in a vicious cycle. Eventually, Venus's oceans boiled away. The water vapor was broken apart by ultraviolet radiation, hydrogen escaped to space, and oxygen combined with rocks on the surface. What remained was a thick atmosphere of carbon dioxide from volcanic outgassing, creating the hell world we observe today. Venus is a cautionary tale. It shows that a planet very similar to Earth can undergo a climatic catastrophe that transforms it into an inhabitable wasteland. The difference between paradise and hell can be surprisingly small. A bit more solar radiation, a bit more volcanic activity, positive feedback loops that spiral out of control. The Soviet Venera landers gave us our only glimpses of Venus's surface. Venera 9 and 10 in 1975 returned the first photographs from the surface of another planet. The images show flat rocky plains littered with angular rocks, lit by an eerie orange glow. Venera 13 and 14 in 1982 returned color images showing reddish-orange rocks and soil,
and even recorded sound, the eerie whistle of wind in Venus's thick atmosphere. These landers survived for only about an hour each before succumbing to the heat and pressure. But in those precious minutes, they gave us something invaluable: ground truth, direct observation, the knowledge that comes only from being there. Radar mapping missions, especially NASA's Magellan orbiter in the early 1990s, revealed Venus's surface in detail. It's a young surface, geologically speaking, probably only about 500 million years old. Something resurfaced the entire planet relatively recently, likely massive volcanic eruptions that covered over older craters. Venus has more volcanoes than any other planet in the solar system, over 1,600 major volcanoes and possibly hundreds of thousands of smaller ones. Whether any are still active is unknown, but probable. There are also strange features found nowhere else. Coronae, circular structures hundreds of miles across where mantle plumes have pushed the surface upward. Arachnoids, named after their spider-like appearance with radial fractures extending outward. And vast highland plateaus, including Ishtar Terra, home to Maxwell Montes, a mountain higher than Mount Everest. Venus is a world dominated by volcanism, by heat, by crushing pressure. It's a reminder that planetary evolution can take wildly different paths, even from similar starting points. Mercury and Venus, our innermost neighbors, both so different from Earth, both inhospitable to life as we know it. Mercury, airless and extreme, its surface bombarded by solar radiation and micrometeorites, its ice paradoxically surviving in permanent shadow. Venus shrouded and suffocating, a greenhouse gone mad, perhaps once a paradise.
Close your eyes and picture Mars. You've probably seen it in the night sky. That steady red point of light, brighter than most stars. That warm rust color that made ancient peoples think of blood, of war, of iron. Mars has haunted human imagination for as long as we've been human. The Romans named it after their god of war because of its blood-red hue. In ancient Egypt, it was Her-Desher, the Red One. In China, Yingyanwo, the fire star. Every culture that watched the skies noticed Mars and knew it was special. But it wasn't until the telescope era that Mars began to reveal its mysteries and create new ones. In the 1600s and 1700s, astronomers observed that Mars had polar ice caps that grew and shrank with seasons. They saw dark and light regions on its surface that seemed to change. Mars, unlike Venus with its impenetrable clouds, offered a view of an actual planetary surface. It was tantalizing. It suggested a world with weather, with seasons, with processes active and ongoing. Then came those canals we mentioned earlier. Schiaparelli's Canali, misinterpreted and elaborated upon by Percival Lowell. The idea of Martian civilization gripped the public imagination. H.G. Wells wrote The War of the Worlds in 1898, imagining Martians invading Earth. Edgar Rice Burroughs created John Carter of Mars, a series of adventure novels set on a dying Mars inhabited by various species. Mars became, in human culture, the most likely abode of alien life. The dream died hard. Even when Mariner 4's images in 1965 showed a cratered, apparently dead world, some held out hope. Maybe the spacecraft had just photographed the boring parts. Maybe life existed in other regions. But as more spacecraft visited Mars, a different picture emerged. Not the Mars of science fiction, but something perhaps more interesting. A world with a past. Mars is small, about half the diameter of Earth, with just 11% of Earth's mass. Its gravity is only 38% of Earth's gravity. If you weigh 100 pounds on Earth, you'd weigh 38 pounds on Mars. You could jump nearly 3 times higher. The atmosphere is thin, less than 1% the pressure of Earth's atmosphere at sea level. It's mostly carbon dioxide with traces of nitrogen and argon. There's essentially no oxygen. The air pressure is so low that liquid water cannot exist on the surface. It would either freeze or evaporate instantly. The temperature averages around -80 degrees Fahrenheit, -60 degrees Celsius, though it can get as warm as 70 degrees Fahrenheit, 20 degrees Celsius, on the equator during summer afternoons, and as cold as -195 degrees Fahrenheit, -125 degrees Celsius, at the poles in winter. Mars today is cold, dry, and dead. But it wasn't always. The evidence is written across Mars's surface in features that can only have been carved by flowing water. Valley networks that look exactly like dried-up river systems. Outflow channels where catastrophic floods once carved vast canyons. Delta deposits where rivers once emptied into ancient lakes or seas. Minerals that can only form in the presence of liquid water. Sometime in Mars's distant past, probably between 3.8 and 3 billion years ago, Mars had liquid water on its surface. It probably had a thicker atmosphere. It might have had lakes, rivers, maybe even an ocean covering much of its northern lowlands. It might have been a world where rain fell from the sky. What happened? Mars lost its magnetic field. Earth's magnetic field protects our atmosphere from being stripped away by the solar wind, charged particles streaming from the sun. Mars once had a magnetic field too, generated by a liquid iron core. But Mars is small, and small planets cool faster. Its core solidified, the magnetic field collapsed, and the solar wind began slowly eroding Mars's atmosphere away. Over hundreds of millions of years, most of Mars's air was lost to space. Without atmospheric pressure, liquid water could no longer exist. The water froze or evaporated. The rivers dried. The lakes disappeared. Mars became the desert world we see today. But the water didn't entirely disappear. The polar ice caps aren't just frozen carbon dioxide, though there's a seasonal cap of carbon dioxide ice. Under the dry ice is water ice, vast amounts of it. There's also ice mixed with soil in the Martian permafrost. And in 2018, radar observations confirmed the possible existence of liquid water beneath the south polar ice cap, a subglacial lake similar to those beneath Antarctic ice on Earth, kept liquid by pressure and dissolved salts. Mars might be dead on the surface, but deep beneath the ice, liquid water might still exist. And where there's liquid water, there's potential for life. This possibility drives Mars exploration. Since the 1960s, we've sent dozens of missions to Mars, more than to any other planet. Many failed. Space is hard, and Mars has earned the nickname Death Planet among mission planners for the high failure rate of Mars missions. But many succeeded. The Viking landers in 1976 were the first successful Mars landers. They searched for life with clever experiments that looked for biological activity in Martian soil. The results were ambiguous and controversial. Some scientists argue the Vikings did detect life. Others believe the results can be explained by unusual Martian chemistry. The question remains open. In 1997, Mars Pathfinder landed with a small rover called Stogener, the first wheeled vehicle to operate on another planet. It was the size of a microwave oven and operated for 3 months, far exceeding its design lifespan. Then came the Mars exploration rovers, Spirit and Opportunity, landing in 2004. They were designed to last 90 days. Spirit operated for 6 years. Opportunity, incredibly, operated for almost 15 years, traveling over 28 miles, 45 kilometers, until a massive dust storm in 2018 finally ended its mission. These rovers found definitive proof that liquid water once existed on Mars. Opportunity discovered hematite blueberries, small spherical concretions that form in the presence of water. Spirit found evidence of ancient hot springs. Both rovers found layered rocks that could only have been deposited by water. In 2012, the Curiosity rover, a car-sized mobile laboratory, landed in Gale Crater. It's been exploring for over a decade now, slowly climbing Mount Sharp, a 3-mile-high mountain in the center of the crater. Curiosity has found organic molecules, the building blocks of life, though not necessarily evidence of life. It's found evidence that Gale Crater once held a lake for perhaps millions of years. Stable, long-lasting water, where if life ever existed on Mars, it would have had time to evolve and thrive. In 2021, the Perseverance rover landed in Jezero Crater, site of an ancient river delta. It carries the most sophisticated instruments ever sent to Mars, including an experiment to extract oxygen from the Martian atmosphere, proving this technology for future human missions, and a small helicopter called Ingenuity. Ingenuity is special. It's the first aircraft to fly on another planet. The Martian atmosphere is so thin that flying is extremely difficult, equivalent to flying at 100,000 feet altitude on Earth, more than twice the cruising altitude of commercial jets. Engineers weren't sure it would work. It did. Ingenuity has made over 70 flights as of this writing, far exceeding its planned 5 flights, serving as a scout for Perseverance and proving that aerial exploration of Mars is possible. But perhaps the most profound thing about Mars exploration isn't the rovers or orbiters or the data they return. It's what Mars represents to us. Mars is Earth's future, perhaps. Or rather, one possible future. A world that was once habitable, but lost its magnetic field, lost its atmosphere, lost its water. It's a warning about planetary fragility. But Mars is also Earth's past. When we explore Mars, we're looking at a world frozen in time, preserving evidence of planetary processes from billions of years ago. Earth's surface is constantly recycled by plate tectonics. Old surfaces are subducted and melted. Evidence of Earth's ancient history is mostly erased. But Mars has no plate tectonics. Its surface preserves a record of the solar system's youth. And Mars might be humans' future, in a different sense. It's the most plausible candidate for human settlement beyond Earth. It's harsh and hostile, but it has resources: water ice, minerals, soil that could potentially grow plants with the right modifications. The day is about 24 hours long, close enough to Earth's that human circadian rhythms would adapt. There are seasons. There is land area roughly equal to Earth's total land area. Visionaries like Elon Musk speak of making humanity multiplanetary, of establishing a self-sustaining city on Mars within our lifetimes. It's ambitious to the point of seeming
There's something different about orbiting a planet versus flying past it. A flyby gives you snapshots, moments frozen in time. But an orbiter gives you something more valuable: context, change over time, weather patterns, seasonal cycles, the ability to target observations, to react to discoveries, to build a comprehensive understanding rather than just catching glimpses. The Voyager missions were incredible, but they were appetizers. To truly understand the giant planets, we needed missions that would stay. In October 1989, the Space Shuttle Atlantis launched the Galileo spacecraft toward Jupiter. It would take 6 years to reach its destination, following a complex path that included gravitational assists from Venus and Earth. During this journey, Galileo made the first close observations of 2 asteroids, Gaspra and Ida, discovering that Ida has a tiny moon, the first asteroid moon ever observed. Galileo also had a front-row seat to one of the most spectacular cosmic events ever witnessed. In July 1994, comet Shoemaker-Levy 9, which had been captured by Jupiter's gravity and torn into fragments, collided with Jupiter. For nearly a week, chunk after chunk of the comet slammed into Jupiter's atmosphere at speeds of 134,000 miles per hour, 60 kilometers per second. Each impact created fireballs thousands of miles high and left temporary dark scars in Jupiter's atmosphere, larger than Earth. It was the first time humans watched a cosmic collision in real time. It was a reminder of the violence inherent in our solar system. and a sobering demonstration of what would happen if such a comet hit Earth. Jupiter, in a sense, protects us. Its enormous gravity deflects or captures objects that might otherwise threaten the inner planets. Galileo arrived at Jupiter in December 1995. But it didn't arrive alone. The spacecraft carried a probe, a cone-shaped capsule designed to plunge directly into Jupiter's atmosphere. On December 7, 1995, the probe entered Jupiter's atmosphere at over 100,000 miles per hour, experiencing deceleration forces 230 times Earth's gravity. It deployed a parachute and began transmitting data. For 58 minutes, the probe descended through Jupiter's clouds, sampling the atmosphere, measuring temperature, pressure, chemical composition. It found less water than expected, detected powerful winds, and measured lightning 1,000 times more powerful than Earth's lightning. Then, about 100 miles below the cloud tops, where temperatures reached 305 degrees Fahrenheit, 152 Celsius, and pressure reached 23 atmospheres, the probe's electronics failed and it fell silent, eventually melting and vaporizing in Jupiter's depths. It was the only direct sampling of a giant planet's atmosphere we've ever conducted. Meanwhile, the main Galileo spacecraft entered orbit. For nearly 8 years, it orbited Jupiter, conducting 34 flybys of the Galilean moons, transforming our understanding of these worlds. Europa became the star of the mission. Galileo's close observations revealed that Europa's icy surface is relatively young. Few craters mar its shell. The ice is crisscrossed with dark linear features called lineae, which appeared to be cracks in the ice that have been filled with material from below. Some regions show chaos terrain, areas where the ice appears to have broken apart and refrozen in a jumbled mess, like pressure ridges on Arctic ice sea. The implication is profound. Beneath Europa's icy shell, perhaps 10 to 15 miles thick, lies a global ocean of liquid water. This ocean is kept liquid by tidal heating, the same gravitational kneading that powers Io's volcanoes, just less intense. The ocean might be 40 to 100 miles deep, containing 2 to 3 times the volume of all Earth's oceans combined. An ocean on a moon of Jupiter. An ocean that has existed for perhaps billions of years, protected from the vacuum of space by its ice shell, potentially containing more water than Earth. Could life exist there? We don't know. But we know that on Earth, wherever there's liquid water, even in the most extreme environments, deep ocean vents, Antarctic ice lakes, miles beneath the surface, we find life. The possibility that Europa harbors life, perhaps simple microbial life, but possibly more complex organisms, drives plans for future missions to explore this ocean world. Galileo also revealed Io in unprecedented detail. The moon is literally turning itself inside out, resurfacing constantly. Its volcanic plumes reach hundreds of miles into space. Its surface is painted in yellows, reds, oranges, and whites, sulfur compounds in various forms. Io has mountains taller than Everest, formed not by tectonic processes, but by compression as the moon's surface contracts. It has lava lakes. It has more volcanic activity than all of Earth's volcanoes combined, multiplied many times over. Ganymede, the largest moon, revealed itself as a complex world with both ancient dark terrain and younger bright terrain. Galileo discovered that Ganymede has its own magnetic field, the only moon in the solar system known to have one. This magnetic field creates a mini magnetosphere within Jupiter's larger magnetosphere, a magnetic bubble within a bubble. Even Callisto, seemingly the most boring of the Galilean moons, with its heavily cratered ancient surface, revealed surprises. Galileo data suggests that Callisto, like Europa, might have a subsurface ocean beneath its cratered ice shell. Jupiter itself showed its dynamic nature. Galileo watched storms form and dissipate. It observed the Great Red Spot and smaller storms, tracked their evolution over years. It measured Jupiter's magnetic field and radiation belts, discovering that the radiation environment is even more intense than expected, harsh enough to gradually damage the spacecraft. In September 2003, as Galileo's systems failed from radiation damage and its fuel ran low, mission controllers made a decision. Rather than leaving the spacecraft in orbit where it might eventually crash into Europa and potentially contaminate that moon's possible ocean with Earth microbes, they commanded Galileo to plunge into Jupiter's atmosphere. On September 21, 2003, Galileo dove into Jupiter at over 100,000 miles per hour, vaporizing in seconds. It was a fitting end. The spacecraft, named after the man who first observed Jupiter's moons through a telescope, became part of the planet it had studied for so long. But even as Galileo ended its mission, another ambitious orbiter was on its way to a different giant planet. Cassini launched in October 1997, bound for Saturn. Like Galileo, it would take years to reach its destination, 7 years in fact, arriving at Saturn in July 2004. Cassini was a massive spacecraft, over 22 feet tall and weighing over 5 tons, one of the largest interplanetary spacecraft ever launched. It carried a smaller probe, Hygiene, built by the European Space Agency, designed to land on Titan, Saturn's largest moon. When Cassini arrived at Saturn, it performed a tricky orbital insertion, passing between Saturn's rings and the planet itself, the only safe path through the ring system. Then it settled into an orbit that would last for 13 years, far longer than its primary mission of 4 years. It would eventually complete 294 orbits of Saturn, 162 targeted flybys of moons, and countless observations of the planet and its rings. But first, there was Hygiene. In January 2005, the Hygiene probe separated from Cassini and plunged toward Titan. For 2.5 hours, it descended through Titan's thick atmosphere, its instruments measuring composition, temperature, and pressure, its cameras photographing the hidden surface. What Hygiene revealed was astonishing. Titan has a weather cycle similar to Earth's water cycle, but with methane. Methane clouds form in Titan's atmosphere. Methane rain falls from the sky. It flows in rivers, collects in lakes and seas. Then it evaporates, returning to the atmosphere to form clouds again. It's the only other world in the solar system where liquid falls from the sky and pools on the surface.